Hi everybody, second to last day of class. This is our last day where we start a new section of material. This is lecture 36, April 22nd. We're starting section 9.4 in Stewart, which is area and length in polar coordinates. This is day 1 of 2. We'll be discussing this again on Friday. All right. Well, meeting part 1, I want to discuss, develop the formula for area. So I'm going to draw some shapes, and I want you to tell me, faster than my first class did, what the area of these shapes is. Raise your hand if you can tell me what this area is. I want a bunch of hands in the air. Yeah. Good. Now, what about this? What's the area of that wedge? Who can help me out here?
I don't know if it's like, but it could be pi r squared times theta over 360.
Yeah, over 2 pi. So area would be whatever the area of the whole circle is times a multiplier, which says how much of the circle have we got. So whatever theta is, divide that by 2 pi. That tells you how much of the circle we've got. If theta is 2 pi, then I've got a whole circle. But this simplifies as, and this should be pi r squared. So this simplifies as pi r squared theta. I'm sorry, it simplifies as r squared theta over 2. The pi's cancel. So again, if theta is the whole circle, then I get pi r squared. If theta is pi, that means I've got half the circle, then my area is pi r squared over 2. It makes sense. Now, what about this? It's up to you. Same thing, but just delta theta. Yeah. So A is r squared delta theta over 2. Now, what about this situation? Suppose I've got a polar curve. So my r depends on theta. And I've got an angle of delta theta. What would that area be? Exactly. So r of theta, in this case r depends on theta, times delta theta over 2. Now, what if I got a bunch of those things? So each of these things has angle delta theta. And I've got a whole bunch of them in between here. So I've got this whole shaded region. Well, this is kind of cheesy, But the area would be, well, each of those things looks like an r of theta squared, delta theta, divided by 2. But then I'm going to add them all up. And so I would do the summation, beginning with the first one and ending with the last one. Now, imagine doing that with smaller and smaller delta theta. So take the limit. As delta theta gets smaller and smaller, closer and closer to 0, well then I'd be looking at this kind of thing. And the area would be, well, it would be the integral instead of the sum. The integral just indicates that I've taken the limit. So r of theta squared over 2. And then instead of delta theta, I write d theta. Again, that just indicates that I've taken a limit. When I was an undergrad, the instructors would say things like, well, those things are infinitely skinny, which would drive me nuts because that didn't help me because I can't imagine something. What does it mean something's infinitely skinny? All this means is we have an expression there, we take the limit, and this means that we took the limit. And then we're going to integrate from theta 1, or from alpha to beta. So from theta equals alpha, so here theta equals alpha, and over here theta equals beta. So there's our formula for area. I'm going to put that way over here on the sideboard. The area is the integral from theta equals alpha to beta of r of theta squared over 2. All right, that's meeting part 1. Meeting part 2 is examples. And in doing these examples, I'm doing kind of a cross-section of examples of types that you'll have on your homework. I've chosen ones that involve a cross-section of techniques. So, example 1. Find the area of the region bounded by r of theta equals e to the minus theta over 4 for theta between 0 and pi. All right, well, first thing we need to do is visualize this region to make sure we understand what we're doing. So we're going to get a picture of the region. So I need to graph the region. I need to sketch the polar curve r equals e to the minus theta over 4. So remember how we do this. We start by graphing r as a function of theta. So we're going to sketch this in the xy plane. But we're going to start by graphing r versus theta. So we got to graph this as a function of theta. Now, I'm going to do this by transformations. Okay, so my first graph, my most basic graph would be r equals e to the theta. What would that graph look like? Graph of r equals, Trent, right, so Trent has made the cheering squad for the math, whatever the event is. So it's an exponential graph. All right, now our next transformation could be r equals e to the theta over 4. So what would that do to our graph? Dividing the variable by 4. Jace? Right, it's going to expand it horizontally. So the action is going to be horizontal, and dividing by 4 means that we're going to, it's going to multiply, it's going to expand the graph horizontally by a factor of 4. So it's going to go up much more slowly. Still going to go through 0, 1. Still going to go through 0, 1, but it's going to go up much more slowly. So what does r equals e to minus theta over 4 look like? Kinsey?
Reflects over the y-axis.
Reflects over the y-axis. So it's going to look like this. It's going to go through 0, 1. This is this is theta equals 0. And r equals 1. There's all sorts of confusion. If you're not confused, it's because you're not paying attention. Because if you pay attention, this is all confusing. Sometimes I display ordered pairs with the r on the left and the theta on the right. But in this case, I'm making a graph of r versus theta. So the horizontal coordinate I put on the left, the vertical coordinate I put on the right. Now, our graph, our curve is that, but restricted to theta between 0 and pi. So theta equals 0 is here, theta equals pi is here. So our curve is this. There's our curve, that red curve. Now let's make a picture of this in the xy plane. Now, it starts with theta equals 0 and r equals 1. Now over here, that's the place where r theta equals 1, 0. When I plot polar curves in the xy plane and I show the coordinates, I put the r on the left and the theta on the right. So this is r theta equals 1, 0. And also, this is xy equals 1, 0. It's kind of wacky. The xy coordinates are the same as the r theta coordinate. Now, it's handy to have a circle of radius 1 as a guide. That circle is the graph of this horizontal dotted line. If the radius were always a constant 1, that would be the graph. But it's not. The radius gets smaller as my angle goes on. So my radius starts that big, but then it gets smaller. And gets smaller and smaller and so forth. And in negative time, the radius gets bigger and bigger. So there we go. So there's our curve. And the region that we're interested in is this region. So again, there's a lot of understanding that comes from slowing down and figuring out how these graphs work. This is all review of stuff we've been doing. Now we're ready to set up the integral, which is relatively straightforward. The area is going to be the integral from theta equals 0 to pi of 1/2 e to the minus theta over 4 squared. Okay, well the 1/2 comes out. And remember that a to the b squared is a to the 2b. So I'm going to do e to the minus 2 theta over 4. So in other words, e to the minus theta over 2. Now remember that the derivative of e to the kx, raise your hand if you know what this derivative is. Oh, come on. You're going to get relegated back to Calc 1. Silver?
K dkx.
Good. So what's an antiderivative of e to the kx? Somebody else. Morgan, your hand was sort of briefly up. What's an antiderivative here? If that's the derivative, what's an antiderivative? Exactly. Instead of multiplying by k, you divide by k. So e to the kx over k. So this antiderivative is 1/2 e to the minus theta over 2, and then divide by the k, which is minus 1/2. And that's my antiderivative, and I need to evaluate that from 0 to pi. Now, I'm going to skip all the algebra here because I want to get through stuff without being crazy. So this is algebra. So there's one little step of calculus. It's calculus knowing to set this up, and then calculus knowing how to do the integral. But then all the rest of this is just algebra, and what you get is 1 minus e to the minus pi over 2. And that's roughly 0.792. So again, I'm not going to dismiss this algebra. You got to buckle up, turn off the TV, turn off Instagram, whatever you have on, and pay attention to the details, and you get to here. Example 2. Find the area of one loop of r equals sine 2 theta. Okay, so we've done this now a couple of times. Anybody remember what this region is going to look like? You need to get a picture of the region. R equals sine 2 theta. Anybody remember how that looks? Jace, was your hand up?
It's the 4 petals.
Yeah, remember that? It's a 4-petal flower. But let's just review this because and you should have had this in recitation also yesterday. So if you sketch the polar curve, we're sketching r equals sine 2 theta. Somebody help me out here. What does this 2 do to the graph of sine theta? Yeah, so it's an accordion being compressed by a factor of 2. So instead of having a period of 2 pi, it has a period of pi. goes up as high as 2, down as low as -2, and it finishes here at pi. So this is pi over 2, and this is pi over 4. Now remember this, I did this in class. You might think, well, you got a whole cycle, you're done, but we have to go out to an angle of 2 pi, because we need to know what to do as that angle sweeps all the way around back to 2 pi. Well, so it's going to go through another one of these cycles. So this is going to be 3 pi over 2, and this is going to be 2 pi. And then remember how we visualize this. The positive R values I denoted with red. The negative R values I denoted with yellow or green, depending on my mood. And then we graphed this. So in the x, y plane, remember it's important to label the axes. This is the r axis and the theta axis. Now we have the x-axis and the y-axis. This is telling us that as the angle sweeps from 0 to pi over 2, r starts at 0, goes as big as 2. There should not be 2. This should be 1. This graph was multiplied, was shrunk horizontally, did not affect the vertical axis. Okay, so it looks like this graph would be helpful to have a circle of radius 1. So as the angle sweeps from 0 to pi over 2, excuse me, the radius starts at 0, grows as big as 1, and comes back down. And it's biggest when you're at the angle of pi over 4. So at pi over 4, the radius is 1, and so it looks like this. As the angle sweeps from 0 to pi over 2, the radius grows as big as that and comes back down. So there's the pedal that we got here. Now, as the angle continues sweeping from pi over 2 to pi, my radius goes negative. So my angle continues sweeping from pi over 2 to pi. The radius grows on the negative end of this, goes out as far as negative in 1 and then back to 0. So my second lobe is here. And then my third lobe is down here. And my fourth lobe is up here. 4-petal flower, as Jace said. Now what we're supposed to find is an area of 1 loop, they call it. Here in this class I was calling it petals. Okay, so we're ready to go. We set up, we see that we needed to be able to visualize this in order to figure out the endpoints of our integration. So the area is going to be an integral of 1/2 times the radius squared, so sine 2 theta. So sine squared 2 theta. But what's my beginning angle and what's my ending angle? Well, for that we need the picture. That loop, that first loop, starts with angle of theta equals 0 and ends with theta equals pi over 2. Okay, well, let's pull the 1/2 out. So here's where you need some trig identities. Now, there are only a couple that I can remember. One, I'm going to come over here on the sideboard and put these trig identities. One is this one. Anybody remember what the formula for sine 2 theta is? Kenzie? Yeah, so let me back up. Something more fundamental. Sine of A plus B is sine A cos B plus sine B cos A. Okay, but if those are the same, if I have sine of 2, theta plus theta, then both of these things are the same, so I end up with 2 sine theta cos theta. Okay, what about cos of A plus B? Jace?
Wasn't it sine A, sine B minus cos B?
Other way around. Cos A, cos B minus sine A, sine B. Okay, well, what if those are both thetas? Then I get cos 2 theta would be, well, cos theta times cos theta would be cos squared theta minus sine squared theta. Now, it looks like this is the thing that would be useful, because what we've got over there on the board is, well, we've got a sine of 2 theta going on. But wait a minute, it's squared. So it turns out that if we try to use this to simplify that thing up there, it's going to make it messier. So we're going to end up using this. Now, these I managed to go through life remembering. If I try to remember anything more than this, I'll forget where my keys are and I won't be able to get home. So, what I would like to do is I'd like to replace that sine squared with something. Well, there's a sine squared here. So I know that I can use this in a couple of different ways. Now let me show you how I do this at home. Again, I don't ever remember any other formulas. I abbreviate this one as C2 equals C squared minus S squared. So cosine of 2 theta equals sine squared theta minus cos squared theta minus sine squared theta. Oh, but cos squared is 1 minus sine squared. So this is 1 minus 2 sine squared. So cos of 2 theta is 1 minus 2 sine squared theta. Okay, well, let's subtract 1 from both sides. So this says cos 2 theta minus 1 equals minus 2 sine squared theta. Let's divide both sides by negative 2. C2 minus 1 over minus 2 equals S squared. Okay, let's multiply top and bottom by negative 1. So I end up with 1 minus C2 over 2 equals S squared. What I've just shown is that sine squared theta equals 1 minus cos 2 theta, all that over 2. I can't count the number of times I've done this in my work this semester, because again, I just refused to memorize this. If I thought I would memorize this, I would either remember it wrong or I'd remember it right, and either way I'd forget where my keys are. So I don't try to do this. I just remember this, and I remember how to quickly do this. And in the homework for this week alone, I've got this calculation written a whole bunch of, actually I wrote it down the first time I did it, and I'm always thumbing back to it. So we've got that. There's an analogous one where instead of getting rid of the cos squared, I get rid of the sine squared. And what I end up with is cos squared theta equals 1 plus cos 2 theta. over 2. So again, these are all trig identities, and for me, my brain filled up here. But these are going to be useful. In fact, that's the one that I want. Sine squared of some angle is 1 minus cosine twice that angle. I'm going to use that one over here. This is going to be 1/2 integral from 0 to pi over 2. And instead of sine squared 2 theta, I'm going to think of my angle as 2 theta. I'm going to have 1 minus cos 4 theta over 2. So I used that formula for the sine squared of something. Well, look, the 2 I can pull out, and I end up with 1/4 in front, the integral from 0 to pi over 2 of 1 minus cos 4 theta. All right, now comes calculus. I have to integrate 1, so I have 1/4 hanging out front, and I'm going to integrate 1, that's going to give me a theta. Integrate cos 4 theta, got a minus sign in front, I'm going to get sine 4 theta over 4. Let's check. Let's take the derivative. The derivative of sine of 4 theta over 4. Well, that would mean I'd pull the 1/4 out, and I'd take the derivative of sine 4 theta. I don't need to use the quotient rule. That would be really silly. And then here I have a chain rule problem. I have 1/4. I have to take the derivative of the outer function. That gives me cosine. Put the inner function back in, and then multiply by the derivative of the inner function, and I get cos 4 theta. So the derivative of this is this, so the integral of that is this. And I'm integrating from 0 to pi over 2. Theta equals 0 to theta equals pi over 2. And here, I'm going to do dot, dot, dot algebra. Because if I do any more algebra, you're just going to all start snoring because you're already half asleep. So the algebra steps are just straightforward, just evaluating, and you get dun, 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 pi over 8. Really cool. Very pretty formula, which is roughly 0.393. So what would the area of the whole flower be? Liam? Pi over 2. Yeah, just 4 of those petals. Example, that was example 2. I erased but didn't write the number. Example 3. Again, I hope you don't mind. I'm going to leave out the algebra because it's just not a good use of class time. The only way you would really, you just need to do the algebra really carefully. Okay, example 3. Find the area bounded by the inner loop of r equals 1 plus 2 sine theta. Okay, recognize this from recitation yesterday? So let's remind ourselves. So we want to visualize the region. We need to draw the region. So let's start by graphing r of theta versus theta. So my r of theta is 1 plus 2 sine theta. Okay, so that's a sine graph, a standard sine graph, that's been multiplied vertically by a factor of 2 and then moved up 1. So there's going to be a new baseline here of height 1, and the graph is going to wiggle up and down from there. But it's going to wiggle up 2 and down 2, up 2 and so forth. Well, okay, I need to make this prettier. That's as far as I need to go, because that's theta. That's one complete cycle of sine theta. That's theta equals 2 pi. Now, excuse me. Remember, keeping my style, I'm going to draw all the positive r's red. Positive as in above the x-axis, or above the theta axis. And the negative r's there. So we need to know what this theta is here. So find those axis crossings. So we're going to find theta where r equals 0, because that's going to be useful when making the graph, the polar plot. So I'm going to turn this around. 0 equals r of theta. So that's 1 plus 2 sine theta. So that means that sine theta is minus 1/2. So what are the angles where that's true? Let's draw the unit circle. In the x, y plane. Here's the unit circle, and we're interested in places where y, so here's, don't complain about my circle. This is 0, -1. Y is -1 here. So we're interested in the places on this circle where y is -1/2. So the question is, what are these angles? What's this angle? And what's this angle? What are these two angles? Andrew?
7 pi over 6 and 11 pi over 6.
Exactly. So theta equals 7 pi over 6 and 11 pi over 6. I hope some of you figured this out in recitation. So come back over to here. This is theta equals 7 pi over 6, and this is theta equals 11 pi over 6. Not quite 12 pi, not quite 2 pi. Okay, so let's make our picture. Now notice that it's going to be useful to have, well, r gets as big as 3 and gets as big as -1. So let's put circles here of radius 1 and radius 3. So this is r equals 3, and this is r equals 1. All right. Well, when we start at the beginning, when the angle is 0, our r is 1. So we start here. R theta equals 1, 0. That's also the xy coordinate. Now, as my angle sweeps from 0 to, this is pi, my r goes up to 3 and back down to 1. So my r goes up to 3 and back down to 1. And then there's a little bit of time where r is still positive until I get to 7 pi over 6. My r is shrinking. So let's put in a little guide here. This is going to be 7 pi over 6. In that little bit of angle space, my r shrinks to 0. And then my r goes as negative as -1, and comes back to 0 by the time I get to 11 pi over 6. So that's here. 11 pi over 6. So as my angle sweeps from here to here, my r is becoming negative, as big as -1, and then back to 0. So again, my angle is doing this, and my r is growing as big as -1 on the back ray and back to 0. So I get this. And then I have this little bit of angle from 11 pi over 6 to 2 pi where my r is again becoming positive. So there's our picture, and there's our inner loop. That's the thing we need to find the area of. All this work is involved really in figuring out these angles. That's the main thing. But visualizing these is useful. So our area is going to be the integral from 7 pi over 6 to 11 pi over 6. Theta equals that. I'm going to have 1/2 my r is 1 plus 2 sine theta squared. Okay, well, let's pull out the 1/2. And then let's square that. I get 1 plus 4 sine theta plus 4 sine squared theta. There we go. Well, look at that. There's our friend from over there on the sideboard. So I'm going to have 1/2 times the integral of 1 plus 4 sine theta plus 4 times that expression from over there on the sideboard. Sine squared theta is 1 minus cos 2 theta. That whole thing over 2. All right. I want to do this carefully. So I've got a 1/2 from 7 pi over 6, integral from 7 pi over 6 to 11 pi over 6. And I have 1 plus 4 sine theta plus 4 over 2 is 2, so I'm going to have 2 minus 2 cos 2 theta. Okay, the 1 and the 2 get together and they have a party, and at the party they become 3. So 3 plus 4 sine theta minus 2 cos theta. We're ready to integrate. Can anybody think of a way to make this integral a little simpler? You're nodding. Does that mean you have an idea how to make this simpler? Well, look how ugly those endpoints are. 7 pi over 6, 11 pi over 6. Geez, do you really want to substitute those in? That's going to be painful. Can we do something with the endpoints? Notice that this shape is symmetric. This is 2 of these things. So So I could integrate either from 7 pi over 6 to pi over 2, 3 to 3 pi over 2. Well, let's just leave it. So when I do the integral, if I try to improvise, I'll screw up. So I get 3 theta minus 4 cos theta. And then I get, this should say 2 cos 2 theta. So what should be going on here? So an antiderivative of this is sine 2 theta. You can check. The derivative of sine 2 theta is 2 cos 2 theta. And that's being evaluated from 7 pi over 6 to 11 pi over 6. And so if I do leave out the algebra trick, what I get is equal to pi over 3 plus radical 3 over 2. And that's roughly 1.913. So again, it's not productive for me to do all that algebra here. That's our third example. We've got one more example, and then we're done. So these last two involve, identifying particular loops. Example 4 is find the area of the region inside R equals 2 cos theta and outside R equals 1. Okay, well, by now you should have you've seen enough of these. You know that this is going to be a circle. It's going to be out on the right because when theta is 0, R is going to be 2. So this is going to be a circle that looks like this. This is R equals 2 cos theta. And then the other thing is R equals 1. Well, that's a circle of radius 1 centered at the origin. So this is the circle R equals 1. And so the region that we're interested in is that moon-shaped region. Now we can think about this by the following. So this is, well, it's this whole region minus this region. If I take this shape, it's kind of like an overflowing ice cream cone set on its side, and I subtract that area, I get this region. So that means in terms of an integral, that means I have a 1/2 r squared for the outer boundary and a 1/2 r squared for the inner boundary. So the area is equal to the integral of 1/2 of the outer r squared, which is 2 cos theta squared, minus 1/2 for the inner r, which is just the number 1. Oh, but we need to know what goes here. So that is, what are the angles where these things cross? Well, let's figure out this one. So figure out theta where the graphs intersect. So I'm going to have the outer radius, which is 2 cos theta, equals the inner radius, which is 1. So cos theta is 1/2. So that means theta has to be equal to pi over 3 or negative pi over 3. So my integral is the integral from negative pi over 3 to pi over 3 of, so when I do this, I get 4 cos squared theta, but it's being divided by 2, so I get 2 cos squared theta. And over here, I get minus 1/2. Now I'm going to do a little bit of simplifying. Notice that this is symmetric. So again, I could get this shape by integrating from negative pi over 3 up to pi over 3, or I could just integrate the top part and multiply it by 2. That'd be nice, because then one of my endpoints is 0. So this is going to be twice the integral from theta equals 0 to pi over 3 of 2 cos squared theta minus 1/2 and d theta. Okay, look, there's a cos squared theta. Over there on the sideboard, we have this expression that we got a while ago. Well, we didn't get it. I got it. I get all the credit. This is what we can do. We can replace that cos squared theta with this. And so this is going to be twice the integral from 0 to pi over 3 of 2 times 1 plus cos 2 theta over 2 minus 1/2. Now look how much this simplifies. Those 2's cancel. So I've got my 2 out front, my integral from 0 to pi over 3, and then I have 1 plus cos 2 theta, and then minus 1/2. Okay, the 1 and the minus 1/2 have a party, and so we end up having the integral of 1/2 plus cos 2 theta from 0 to pi over 2. Now when I integrate 1/2, I get pi over 3. When I integrate 1/2, I get theta over 2. And when I integrate cos 2 theta, I get sine 2 theta over 2. Double check. If I take the derivative of this, I really do get cos 2 theta. And then I have to evaluate this from 0 to pi over 3. And then there's a 2 out front. And again, I'm going to do my famous trick of skipping the algebra. And I get pi over 3 plus square root of 3 over 2. And this is roughly equal to 1.913. So algebra, I skip. So they all start to look the same in that you visualize the graph. This one was pretty simple. You know, the earlier ones I visualized by making a graph of r versus theta and using that to plot the flowers or whatever. You get the shapes, and then you set up the integral, and then you're done. Oh, let me hand back quizzes. Thank you all. So, Gabriel, I'm done.